Again, welcome everyone, everybody. This is the fourth session on turbulence modeling. So we were left off at the instantaneous equations last week, if you remember. And these set of equations completes all the equations that we deal with when we want to simulate a fluid flow. And what we want is to obtain a distribution of all these parameters: velocity, pressure, energy, temperature, and entropy. That is our objective when we are solving these equations, actually, all of these equations. So, distribution of velocity, pressure, energy, density, temperature, entropy. Of course, the flow field could be very simple, like what you have in a laminar pipe flow case, or it could be very complex, as you might see in a in, in a kind of turbulent flow in a multi-stage compressor of an aircraft engine. So far, we have reviewed equations of motion in fluid flow. Now, we're going to start slowly going into more details. For example, we never talked about the stress tensor, sigma ij. And I just told you that it's a stress tensor. Then question arises that what is that, and does it have a physical meaning? What kind of components does it have? So now we are going to dig into more details about this tensor. Mathematically, sigma ij is present in the equations, but we have some physical knowledge about the stress tensor as well. Similar to solids, in fluids, sigma ij is a symmetric tensor. So when a tensor is symmetric, it means that sigma ij is equal to sigma ji. And it's a second order tensor. So because you have two indices, I and j, so you can actually, by going back to the previous week, you can decompose this into its components. So what are the components of these? The first part of decomposition, which is this part, is the deviatoric part. So this is the deviatoric part. And this part, which is 1/3 of sigma kk, when you see these, it means that it is a trace. So this is a trace of a stress tensor. Actually, this trace is nothing but minus normal pressure, so pressure forces. Generally, in fluid mechanics, we represent the deviatoric part of a stress tensor, that is sigma ij. We represent it by tau ij. So we can write the above equation like this form. So sigma ij is tau ij minus p delta ij. Now we can apply this sigma ij into all flow equations of motion, into these equations of motion. I will just give example of that. For example, in thermal energy equation, this equation, the thermal energy equation, you have du dE dt, rho times dE dt plus rho uj dE dxj equals to, so when you look back into this equation, you see it in here, sigma ij. So you will replace sigma ij by tau minus pressure. There is something interesting with the thermal energy equation, and that's why I started to play with the thermal energy equation at first. We also know that for velocity gradient tensor that you have, dui dxj is the summation of the rate of strain. You remember this from last week. This is a symmetric tensor. You have the rate of rotation, which is antisymmetric. And you remember that this part was the isotropic part um, of the velocity gradient tensor, which was equal to zero for incompressible flow. So the right hand side of the equation that we have in here, the right hand side of equation 3a, I can write it as minus p um, dui exj plus, so where does it come from? See this thing, if this operator delta ij acts on dui dxj, uh, I'm sorry, it will be dui dxi. So this operator says that convert any j to I or any I to j. So you will just convert one of these. So dui dxj will be dui dxi or duj dxj, it doesn't matter, plus tau ij times again dui dxj, which is now sij plus tau ij omega ij minus dqj dxj. So this part, we just said that it's because of the delta ij that we converted this j to I. In this second term, you have the deviatory part of sigma ij that represents the shear effect. Uh, so it is like a shear force, okay? So you have some kind of force, tau ij, and then you have the strain tensor. A strain is like deformation, okay? And the deformation is just, you can think about the deformation like the distance. So you have a kind of force times distance. So you remember that force times distance was a kind of work. That's why we call this as work done by shear forces. Again, you have the symmetric tensor tau ij times pure rotation, which is anti-symmetric tensor. And as an exercise, you can show this, that this will be equal to zero. So this will be your exercise. Show that the multiplication of a symmetric tensor like tau ij by an anti-symmetric tensor will be zero. And this part is actually your heat flux. So in here you have your heat flux, and it's kind of that. So what are the interesting stuff that I just told you in here? First of all, in the first term, you have minus p dui dxi. So if it is dui dxi, you can somehow say that if the flow is incompressible, what will be dui dxi? So for incompressible flow, this will be zero. But for high speed flow, or meaning that if your Mach number is very high, it will be significant, okay? And you cannot neglect this dui dxi. The second term, we said that physically it represents the work done by the shear forces, and then we have the change in temperature or energy. Let's say in here we have the change in the temperature or energy in the left hand side of this equation. And so it says that if you kind of deform the flow, see, look at the second term, it says that if you kind of deform the flow by this mean strain, um, actually it affects the temperature or energy of the fluid. The third term, we already said that it is a multiplication of symmetric tensor with an anti-symmetric tensor. It will be zero, and mm, as your exercise, show it. And as a hint, you have to use the property of anti-symmetric tensor. So anti-symmetric tensor like omega ij, one property of this is that it is equal to minus omega ji. So you use this to show that will hold. This will be equal to zero. So after this simplification, your equation, this equation will become this equation that I wrote in here. So this is the left-hand side. It is all there. The right-hand side will be all only tau ij, sij minus dq dx. The equations actually tell stories to us. You don't have to memorize these equations. Uh, Specifically, this equation, the last equation, tells me this story. If you do some shearing work on the fluid, and if you apply some heat, fluid temperature, this represents the temperature energy. Fluid temperature will change. Its temperature is changed such that it will be distributed in space. So this is the convection term, and it will be distributed in time. These are the physical interpretations, which I call them as stories. So the story of this equation is what it represents, what interprets. This is how also people work on turbulence modeling. You will see more complicated equations, but each and every term has a physical meaning in those equations. The terms are there to represent some physics, and we are not dealing with pure mathematics. We are engineers, so these relations represent real physical phenomena that are happening. So if I apply sigma ij to momentum equation, let's go back and see there is the momentum equation in here, and this is the sigma ij there. So I'm trying to apply the definition of sigma ij, which is tau minus p, to the momentum equation. What will I get is this. So for incompressible fluid, or for incompressible flow, I have rho dui dt plus uj d ui dxj is equal to minus p dxj plus d tau ij dxj plus fi. And I is a free index and is from 1 to 3. Now we have pressure in here, which is more or less normal stress acting on the fluid element, and the shear effect is due to this viscosity and the tau. Of course, these are very low-level explanations. So what is shear? Why do we have shear? We may not have shear. Actually, in principal axis, you don't have shear. Everything is normal. So when you were undergraduate, we didn't talk about these things because we were already confused you enough in fluid classes. And if we start talking about the second order tensor and principal axis in which there is no shear, your end will not be very pretty, actually. Now, because you are graduate students, we will go further. So, about the stress tensor, we want to solve these kind of equations, like the equations that you see in here. We want to solve these equations, but we still don't know, for example, how to calculate the tau ij. We don't know what is it. We know that it is related to viscosity and viscous effects in the fluid, but what's the equation? Could it be like tau ij, let's say tau ij is equal to viscosity times cosine of theta? Will it be like this? I want the what is the actual function? People uh, naturally have thought about it for many years, and um, we know that it is tau ij, so it is a second order tensor, so it does have properties relevant to second order tensors, and we need what we call it as a closure. So we need a closure on tau ig. This is not related to turbulence closures. I'm telling you the things that people had thought about in 19th century and how to model the stress and stuff. So what is the function of tau ij? In other words, how can I calculate tau ij? We should we just showed you that this is a second order tensor. So as a second order tensor, I use two tilde sign. So tau, and I'm gonna find this function. Is it a function of mean velocity? Is it a function of pressure? Is it a function of temperature? Is it a function of a strain tensor? Mean strain tensor? Let's see. We know that in solid mechanics, people relate the stress. Actually, they calculate stress based on strain. Solid people relate stress to strain through some coefficients, if you remember. The question is that should I do the same thing in fluid or I cannot do it? There are certain physical properties that restrict some of these parameters. For example, uh, first of all, tau cannot be a function of uh, velocity, mean velocity. The reason is a general physical principle which states that forces, so the tau is kind of stress and it is a force per unit area. So there is a principle that says that forces cannot be function of velocity, or that's something we know it as a Galilean invariance. What does it mean, Galilean invariance? It is related to physical systems being dependent on frame of reference or on motion. When we are talking about velocity, so u bar, this velocity u vector, not bar, this velocity is a parameter that it heavily depends on frame of reference, right? So if you observe a car traveling at 50 kilometers per hour, but you are when if you are inside the car, you will measure your velocity as 0 kilometer per hour. So velocity is frame of reference dependent. The Galilean invariance says that forces cannot be frame of reference dependent. If something is not changing with respect to change in frame of reference, it is called Galilean invariant. For example, if I measure some force, for example, 10 kilonewton to my computer. For example, I will push my computer, uh, let's say case or tower. I will push my monitor with 10 kilonewton vertical force. The question is, if I take this monitor and put it in the back of my, let's say, truck, or let's put it in my car, and then start traveling at 200 kilometers per hour, and I still pushing it with 10 kilonewton, does the force changes? No, it won't. Or is it going to remain the same? Yes, it will remain the same. You can intuitively say that it will remain the same. So forces are frame of reference independent. And therefore, stresses which are related to forces cannot be a function of velocity because velocity is frame of reference dependent. Is there any question? Did you understand this Galilean invariance?
I'm trying to understand, yeah.
Yeah, you're trying to understand after all. Uh, I know these. You should work on these and
Yes.
try to just keep following what I'm saying.
Yes, I need to study more to be able to ask questions.
Yeah, of course, of course. So the second question is that could it be a function of rate of rotation? So in order to do that, you can see this figure that I'm giving in the right hand side. For example, see the translation A part. So a particle is being translated. Translation is also known as rectilinear motion. Okay. Again, your tau cannot be a function of rotational motion. So what is rotation? Rotation is like this. You have an element and you just rotate it. You do not deform it. Because of the fact that rotation does not involve any deformation. So you only rotate it. Shearing does involve deformation. So when you shear something like in D, it is changing, it is deforming the shape of the fluid. When you shear things, their shape will change, like what you see in C part and D part. But as we defined the rotation in fluids, the rotation will not change the shape. It is just a rotation about the fluid element axis. If there is a square, like in B part, you take it, you rotate it in some degrees, and it will still be a square, and it does not become a parallelogram or a rectangle or something else. So, a stress generation requires deformation. Always keep it in mind. When there is deformation, actually, a stress will happen. So, this tau again cannot be a function of rotational motion because rotation does not create any deformation of fluid particle. Using these physics-based reasoning, people have thought about, okay, then how to calculate tau. And at the very end, the results show that it's a good idea to calculate your tau only as a function of strength. So uh, the same as in solids. Okay, so it is a function of a strain. A strain, by the way, is not a velocity. You know this. A strain is Galilean invariant because it is involving gradients, not velocities themselves. So it is defined by 1 over 2 times dui dxj plus duj dxi. So ui, this ui in here, changes with respect to frame of reference. But what about the gradient of ui? So if you write, let's say, du dx, just one component of ui, then I just want to show you right now that the gradient will not change with respect to frame of reference. Just consider one component of this dui dxj, which is du over dx. If you start traveling with some, let's say, constant velocity that is uc, Your velocity gradient then will become, you can write it as d. So u minus uc over dx, right? Because you have this velocity u and you have frame of reference velocity uc, so your absolute velocity will be u minus uc. And you can write it as du over dx minus duc over dx. I just said that if you travel with constant velocity, so your uc is constant, so its derivative is zero, so you will be having again du dx. So on a frame of reference that is accelerating or decelerating, there is complete different story. I'm just telling you the story on a frame of reference that is moving with constant velocity. Therefore, this velocity gradient dui dxj, which is used to calculate my strain, is something that is Galilean invariant. So we can use the strain in the calculation of stress.